Good morning. Welcome to lecture number 7. My name is Carlo Fischione, and today I have the pleasure to give this lecture where we will put emphasis on trade-off between computation and communication. This lecture, it's a special lecture perhaps a bit more special compared to the previous ones because it's including a selection of subjects that is very much in progress right now as I'm speaking. So in these months people are producing new research products, new publications, and this is therefore a selection that is in particular Hossein has done on the subjects of today's lecture that reflects some of the important research trends that is going on. So, but at the same time, it's by no means a complete overview of communication, computation trade-off in machine learning over networks. But if I can say so, it's just a grain of salt and it's the beginning of a story that still has to be written. And maybe some of us here, some of you, will be contributing actively in these research directions. So what I wish you will remember today at the end of this lecture is basically three simple questions here. What is a general framework, primal-dual approach to solve in a distributed setup most common machine learning problems? And this general approach, this setup, is somewhat alternative to the lecture that we had, the previous lecture, to ADMM, that has been extremely successful method, and but yet when it comes computation communication over networks, ADMM has some drawback, and this is so if we can have something more general, more efficient, exactly is the answer to this question here. Then the second question that I wish you should be able to remember today is when the transmission among processors of the network, or if you like, the nodes of the Internet of Things, or devices, maybe sometimes communicating over wireless, when this transmission happens with quantization, which is the most natural thing that can happen, how is the computations of the optimizations used in machine learning, how is this affected? How the quantization has an impact? And this is this question will be done in the case of gradient descent algorithm and in the case of stochastic gradient descent algorithm. These three learning outcomes are then taken from three related publications that are listed at the end of the slides. So the outline of the lecture is therefore divided into the three main questions that I've just mentioned to you, and this computation communication trade-off in a general approach, quantized distributed gradient descent, and parallel quantized stochastic gradient descent. Okay, let's just to put now today's lecture in the context of the course. Let's have a look at what we have seen in the previous couple of lectures. In those last two lectures, we have entered the core part of the course, which is the network, the modeled as a graph, in this case a linear, a grid, a star, multi-star here topology. And we have seen that this could be nodes of Internet of Things, this could be processors, and what is interesting for us is particularly the presence of these communication links and how they can affect the machine learning task. And in the previous two lectures, in particular, we have seen in lecture 5 machine learning problems over so-called master-worker networks, which is this kind of networks, master-worker networks, or simply star networks. Master worker, it's usually is a term used into the machine learning optimization community. For those who work in IoT and communication, we would use this as a star, call this as a star network. And we have seen duality methods for these networks, and in particular, this extremely successful method, the alternating direction methods of multipliers, that was somehow invented around the 50s of the 60s, and then rediscovered around 2006, and then made public in 2000, and it became very popular in 2010, 2011. And I believe that the rediscovery in the electrical engineering community has to be attributed to Professor Giannakis. And then Professor Boyd later and their group, his group, in 2010 has written a comprehensive overview on ADMM that was presented in last lecture by Yuan Gadimi. When then we go from the star network here to the more general networks such as these ones, this step can be done relatively easy thanks to, if you like, a trick, which is the consensus, introducing the consensus constraint, and then we just plug it into the formulation of dual methods and ADMM, and then this allows us to solve common machine learning problems over general networks. And clearly there is trade-off in terms of times that it takes for convergence in the distributed computations, and the topology of the network, and we have also seen some computation trade-off in the previous lecture. Today we go on in this line, and we extend, so we restart precisely from here, and we see a more general alternative method to ADMM that has common points, but can be more general. And we start with the first topic here, which is computation-communication trade-off in a general approach. General in the sense that is more general, potentially more general than ADMM. Okay, let's start with some important definitions, and I'm sure you are already pretty familiar now with these, but let's go over them. And also I've tried to keep notation similar to the previous lectures, but it's not easy since this lecture is taken from various papers. Each paper has its own notation, and it's always a challenge. So we have seen the notion of L-Lipschitz continuity. So a function is a L-Lipschitz continuous if it's such that the module of h of u minus h of v is less than L for the norm of u minus v. And then it's important here to remember the definition of L-bounded support. This function is said to have a support L-bounded if we have that when h of u doesn't diverge, then u is less than some capital L, less or equal to some capital L. Then we have the definition of 1 divided by mu smoothness, and a function is 1 divided by mu smooth if it's differentiable and if the derivative is 1 divided by mu Lipschitz continuous. So in other words, 1 divided by mu smoothness means that we can upper bound a function h of u in this manner. And this upper bound here depends on the mu, so 1 divided by mu, that's why 1 divided by mu smoothness. This upper bound will be extremely useful for the derivations of the convergence results in these distributed communication computations machine learning tasks. So all the proof in the end is a reiterated application of this kind of inequality, together with the other inequality of mu strong convexity. A function h is mu strongly convex if this inequality holds, where here we have to note the two terms, mu, and that's why the mu strong convexity, and s, where in general this s is a subgradient of h at v. Wonderful. So that's what is interesting, is that equipped with this knowledge, just with this knowledge, we can derive all the results that I am presenting in the lecture. And if you have time and interest, you yourself, you can go across the proofs. Good. Then now let's finally, given these definitions, that is all we need to know to live in this world, let's go with the presentation of this general framework. So we in general, we are interested in solving this kind of machine learning problems where we wish to minimize this function here, overall function, which is given by the sum of two other functions, and typically L of u, that is a loss function. It's a way to measure how far or how close are to some points. And then we have another function R, the regularizer, which often we introduce in machine learning problems to take into account of outliers, sometimes missing of information, to penalize certain points. So this is a very general machine learning formulation here, and this actually covers all the problems that we have seen in the course so far. Soon I will give you also examples. This minimization apply both, this notation that I'm using here, in theory I would be missing a parenthesis, so this minimization applies to both, okay? It's not just to L. Now typically also what we do in this lecture is that the loss function is written as a sum of other function Li for some I, so it's a divisible function. The loss function is a divisible function, and it's somehow it makes sense in very many IoT modern machine learning problems distributed over networks and nodes. And then we have the regularizer that in general could be something like this. This formulation is so general, as I mentioned, that includes support vector machines, linear and logistic regression, lasso, and sparse logistic regression, to mention some of the machine learning problems that are modeled exactly in this manner. Now, the idea is that first of all, we will map this problem formulation, this initial problem formulation that I'm calling capital I here, and I'm using the same notation of the paper that I'm using for this lecture. This notation is mapped into, this problem formulation is mapped into two alternative problems, capital A and capital B, that are equivalent to the first one, in the sense that if we have the optimal solution of this, we can immediately recover the solution of this, and at the same time, if we get the solution of this, we can recover the solution of this problem. This is called minimization of big O of A of alpha, and here we are minimizing for alpha, and this is minimization of big O of B of W, and the minimization is W. And there is a one-to-one mapping between L and F and R and G. So this F becomes the loss in general, and G is the regularizer, and in the formulation A. And this is called, therefore, since this is just a mechanical mapping between the two, this is the primal problem, because this was our primal problem. This problem here, B instead, it's called dual problem because the function f star and g star, these are the convex conjugate of the function f and g. So this is nothing else but the dual of this. Although the equivalence between the two problems, it comes using the notion here of convex conjugate, comes as an application of the so-called Fenchel-Rockefeller duality. It's a broad general class here for duality methods, but we don't have time to go through that. Here the assumption is that now this alpha that corresponds to basically to the u here, this alpha and w, these are our decision variables, and we have the matrix A, capital A, that is divided into columns, column 1, 2, and a small n, and there are n columns. So these columns are called X, and I'm here consistent with the notation of the paper. In general, this A is the data matrix, and it's something that it's in general is known. And we will see that in the application of of this method, the columns correspond to the features of the machine learning problem, or the rows could correspond to data for training. Good. Then using now in general the Fenchel-Rockefeller duality, the problem capital A and capital B, they are equivalent, and in particular we can recover the solution of, for example, B, if we have the solution of A with this simple expression. So the W is the gradient of F computed in capital A alpha, if alpha was the solution of problem A. And these two problems, also since as you remember from duality, from the primal, and the difference between the primal and objective and the dual objective gives us the duality gap, that is a function of how good is the solution that we can achieve out of this optimization. It's very useful to have again this difference, the duality gap, because in general we have this inequality that if we have an alpha that is some solution to the problem capital A, it will be such that the objective of that problem is larger than the objective at the optimum. Here alpha star is the optimal solution of problem A, not to be confused with the convex conjugate of alpha, which doesn't make sense here. It's okay, this is star is the optimal solution, not a convex conjugate. And then in the dual we can write the same inequality, and if I just go one slide back, here I have a minimization. If this were written in the usual way the dual is written, I should have a maximization. But in this F star and G star, we do a change of sign, and we still have a minimization. So in such a manner, if I go back here to the duality gap, we have that the objective of the problem B computed in some W, which is not optimal, is of course worse than the objective of the problem B computed in the optimal. But this chain on inequality now is very useful, because we can, in the distributed computations that we use to solve the optimization problem I, we can use these chains of an inequality to say how good is the optimal solution that we are computing. Also it's interesting to note that in general, if the function, if the original in the problem A or in the problem I, the first starting problem, the function G was separable, it stays also separable in the problem B, in the dual. And this is a simple algebraic will be passages to show this fact. So if I go one slide back, if this is a separable function, also the convex conjugate will be a separable function, which is very useful for our computations. And I have taken here a table from the paper that, in my opinion, is very pedagogical because it shows that this general framework now is actually general, and you can apply it to least square problem formulation with the loss, for example, and regularize could be the elastic net, or could be the loss here, could be the logistic regression, and the regularize could be this L2 norm. Or the loss could be, we could have a support vector machine and B and L1 norm, and so on, and all various combinations. So this is just a table that contains examples where we can have the problem for I, and we can write it in the formulation capital A or capital B for many cases. Curiosities or questions so far? Demonstrations? No. If not, then we can go on. And okay, reminding what we wish to do now. I mean, what is our goal here? Is from this general problem formulation that I have posed. The idea is that now we wish to have distributed computations that solve that general problem formulation. So the assumption is that the data set A, capital A, the matrix capital A, is distributed over capital K machines according to some partition. So it's in this partition we are taking some columns of A that might not be even adjacent columns. Could be this column here, and this column there. Might not be adjacent. We group these three columns and we associate them to a processor K. We do that for the number of columns and association, and we have therefore a partition. We call it the indexes of this partition as matcal pk for k1 to capital K. So this capital K is in general less than or equal to the sum, the elements that are in the sum for the function g. So with this we adopt therefore the notation that the vector alpha that was the decision variable of problem capital A is also parted, and we make this notation alpha of K, and to say that it's a vector with the elements that are the same as alpha I, the same elements of this, if the element I was part of the partition and 0 otherwise. So alpha K, they have the same size of alpha, and it's just a vector that contains the element of alpha that belong to the partition K. Then once we have this partition, we also do another partition that we do, and we denote from the column of A. We define another matrix AK that is identical in the size of A, except that it will have 0 in all the columns that don't belong to the partition, and the columns that belong to the columns of A that belong to the partition, they are identical to A. Good. So this is just a notation, and just to fix our idea. So what we wanted to do is to find the minimization with respect to some u of L of u plus R of u. This was problem I, and then we have given the primal and the dual, such as minimization here of alpha of O A of alpha, or minimization of O B of W. These are the two, and here we're looking. This is problem A, and this is problem B. This is one-to-one mapping here, and this is just the dual. Further, now we are saying that the data are partitioned, and there is a number of nodes or processors. For example, processor, this other processor 1, processor 2, processor capital K. This is a capital K. And this processor will have associated a vector alpha k that has the same size as this vector, except that it has 0 if in the elements that don't belong to this node 1. So this is actually alpha 1, alpha 2, and here some alpha k. And yeah, so this is just to be right. This is, so here we will have n1 elements of the matrix capital A. Here we will have n2 elements and n2 columns of the matrix capital A, and here n columns of the matrix A. We have parted the matrix according to this partition here. Okay, now the question is that these nodes, that could be the nodes of an Internet of Things system, or could be its processors, they wish to solve this problem in a distributed manner, exchanging as little information as possible. Okay, now we are at the core of the lecture, in the sense that now it's really important that we wish that what is exchanged among these nodes should be somehow efficient and should consider there is some communication network. We have already seen this setup, is the ADMM also setup, but we will see that that setup has a couple of drawbacks compared to this more general setup that we are studying today. Such as in the classic ADMM, there is a global variable that has to be updated by everybody, and okay, that's bearable. But then there is also a step that is usually called the proximal step, that is also a global step. It's not a step that can be easily distributed, so one would need a third-party entity that recomputes the coupling global variable in a DMM, and that also this entity does also the proximal updating, which instead we don't have here. So that's why this is a more general method. So our main objective here is to distribute the computation that will find the optimal solution to this problem. In the case of the function g, here, the second function that is usually associated to the regularizer that is inside here. So remember that now alpha, this O is given by the sum of two terms. There is an F plus a G, and this is there is this immediate correspondence. Okay, the function G is usually about our assumption, and it's also natural. It's already distributed by assumption because it is given by a sum. The problem in general is that this function f is not distributed. So we cannot associate this function to the processors or to the nodes of our network. And ADMM as a way, clever way to distribute the computations. But here we will use in the general framework another idea, which is to approximate this function with something that is separable. And with the components of such an approximations, they are associated to the nodes, and they can run then the distributed optimization that will solve the machine learning problem. But what is good and is remarkable is that with the assumption that I given you in the beginning, with the list of assumptions, such an approximation works fairly well in general. And let's see what is now this approximation. Now the question is that we wish to have an approximation of this capital O of capital A of alpha, that is the function down here. Can you see here on this? We wish to do an approximation that is separable. And once we have done such a separation, everybody is happy, because this node as a function, this node as a function, this node as a function, everyone will do its own optimization, and fantastic and wonderful, we have solved the problem. So everything here in this general approach will consist in finding an approximation that is separable and is meaningful, which is what is written here on the board. So the idea is that, first of all, let's make this definition V equal to capital A alpha, and we also divide the alpha k, this alpha here, 1, 2, 3, in this special manner. It's an alpha k at some previous step, I am introducing steps here, plus a gamma delta alpha k. And in this definition that I've given, I have not been speaking yet of any steps or iterations, but there will be steps and iterations, and that's why I have t plus 1 and t. But so far, take this as just a variable definition, and suppose that I will be doing optimization over this alpha k t plus 1, that has a heavy notation, because I need it for doing iterations later on, although so far you have not heard of any iteration, okay? So far, just let this be a variable that has a heavy notation. It's just a variable. Yes?
If I understood correctly, you divided that A matrix to some alpha 1 to alpha k. And how do you choose this number of k, and how do you divide this partition?
Excellent questions. Yeah. So the question here is, when we are given the original matrix, data matrix A, how do we associate the columns of the matrix to the nodes here, to the processors? This is up to somehow to the user here. It's up to you. It's up to us when we have our specific problem at hand, how to do the partition. In practice, in IoT. Internet of Things application, we can think that these are real nodes, okay? It's a sensor, and the sensor has a set of data. So everything is already parted. And then this is now a general mathematical framework that abstracts such a natural partition that is already existing in the IoT, in an IoT system. Instead, if we take the perspective of distributing the computation of a processors, so that these are not any longer nodes, but these are simply processors, we can do a partition that could take into account, for example, how this processor is more powerful than the other processor. So we can give a bigger partition, this alpha could contain more element than to the other. But so far, so a partition is something in general. It's up to us to decide, given our problem at hand. Anyhow, as I mentioned, these are fantastic questions, because one could ask, in general, if I have a given number of sensor nodes here in an IoT system, or if I have a certain processing units, is there any optimal partition that I can do so that the computation is as minimum as possible, as little as possible, and the communication is reduced? Okay, that's a fantastic question, and we could write a publication of that, because so far there is no answer to this. Excellent. Any other questions?
For different sensor nodes, they have the similar data set. That means they have the overlapped data set.
Yeah. We can have, absolutely, there is no restriction in this regard. So in the case of IoT system, could be that a node is observing and this data set about a phenomenon that is very similarly observed by another node, we would have a redundancy of data, and yes, there is no restriction in this regard. Yes, can be some form of duplication or observation. And also that's this interesting question here. Let us think that the nodes here, now we are assuming that the matrix A, capital A, it's known and it's perfectly known, okay. But it could be also a form of random matrix, because measurements could be the result of some random observation. So that could be a random, can be a matrix that is, it's just the outcome, it's an outcome of a random variable. This case is not considered in this paper. That is one of the most recent studies in the area. So here again we could write, could do an extension. And this goes back to the beginning of the lecture where I said, look, this is very much ongoing research direction, and in my opinion, exciting research direction. Because as these ideas here, they can apply to a very broad broad spectrum of application, from Internet of Things, big water distribution systems, smart grid systems, but also future communication system. There will be revolutionary communication systems based on some concept of spectrum sharing, and then of course on medical problems with data sets that are distributed among patients or hospitals, and so on. So it's a major exciting research direction. Yes, please.
Does it matter if the input is random at the beginning, because at the end it would still converge, as in with each iteration it's still calculating and sharing the information, so
right.
The duration is more.
Right, it's a good question. So if it happens that, the question is that if it happens that the matrix A is random, will this matter in terms of convergence results here? And the answer is no. Still we would have convergence. But you might question, or how good is the optimal points that we derive? And the answer to this question is similar to least square or minimum least square. You can have, if you have some knowledge on the distribution of data, you can do something better because you have more information, right? And that's, okay, so here we can have another research product exactly to answer this question. Very good. Other curiosities, questions? If not, we go on. And finally, good. So again, I have problem I here, and is not separable in this form, in any whatever formulation. It's in a general sense, it's not generally separable. We now make an approximation of capital O A alpha such that it becomes separable, and this is the separable approximation. It is just this, that if we look closely at the expression of capital O A of alpha, we insert this variable redefinition that I've done with this ugly notation here. I mean, it's the best that we can do. There is no better notation than this, and for our purposes, we just insert, and it's just now will be an algebraic exercise. You insert this definition of the alpha with the partition that we have done with the matrices, and we get this expression. So this piece here, look at the circle that I'm doing, is this piece here is exactly, perfectly capital O of A, completed in alpha, using all the assumptions that I started with, assumption 1, 2, 3, and 4. And there will be for sure, under those assumptions, there will be for sure a set of delta alpha, some gamma here, and some sigma prime, and some tau, that will give this expression. And it's a perfect, this is not even an approximation, it's just a perfect rewriting, and it can be also written further in this manner. So this O, capital O A alpha is this, can be rewritten in this manner as the sum of capital terms, each associated to a function gk sigma prime, where this function gk takes as input delta alpha k, v is the only global vector, and alpha k. This delta alpha k and alpha k, they are local, and this is global. This is the only global variable that is coupling now the k, capital K terms. So now this node here will own this g, this node here will own g2, and so on. And in particular, if we look at the expression of gk, looking at this part, can be rewritten in this manner, in this long manner. Here everything is local, in the sense that what is in this expression now belongs to node 1, 2k. I mean, this k is associated to node, this is will be g1, node 1 would have g1 sigma prime, node 2 would have g2 sigma prime, and so on. And everything is local here, except one thing, that is this v. This is a v, it's a global value, it's the only global information that now is coupling the various nodes here, the various parties, and is the only thing, therefore, that will have to be exchanged when we solve this optimization problem. Because now the idea is that we use this expression to solve a local optimization problem. Every node will solve a minimization of this function here, only of this function gk, then exchange the v, the coupling variable, to the other nodes. The other nodes will do their minimization, everybody keep doing like this, and in the end we will converge to the optimal solution. Okay, to go from here to here, it's just it's really a tedious algebraic work. Okay, tedious algebraic, using assumption 1, 2, 3 that I mentioned in the beginning of the lecture. There is no major, no fundamental theory that you have to take from who knows where. It's trivial algebra and rewriting. So I will spare you to, if I write that on the board, it will take 1 hour just to show the details of these derivations. Next, good, if you have been now following me, so the idea is that the function, this function here, capital O of A, can be divided as a sum of this gk of sigma prime. And therefore, at every node, 1, 2k, I will solve this optimization, where the only variable that I am looking for is the delta alpha k. I will only look for this delta alpha k that minimizes this problem, because if I go back one slide, is the delta alpha k here. But in doing this now local minimizations, using this decomposition, we lose something, because this decomposition here is a true equality, that is this sum of local functions is actually corresponding to capital O A, provided that globally we can find the delta alphas that give this decomposition. But if I decided to do instead a local choice of the delta alpha, it's not any longer a global, and therefore this is not any longer a perfect equality, we would have an approximation. So that's why now what is interesting here is that in this minimization that are done at every node, so this node here will do minimization of delta alpha 1, this node will do a minimization, and here actually g k sigma prime. Then this node will do the minimization of delta alpha 2 of g2 prime, and so on. And I see that there is a typo here, the squared parentheses are missing. I will correct this later, so this should be this notation. So every node will do this independent minimization, will exchange the v, everybody keeps doing like this iteratively, and we hopefully will achieve convergence to the optimal solution. Now, to achieve convergence is not obvious here, because this now are individual minimization, where we individually will choose the delta alphas. We will get the result of these delta alphas that are not given by a global, this global choice of the delta alphas that gives equality. So in other words, the result of the minimization will give approximation of this, but still we will get the optimal solution. If we didn't get an approximation, if this minimization would give the perfect delta alpha here that ensure this equality, then we would have done, because everyone would optimize perfectly and would give the perfect delta alpha that enters in this equality. But it's not the case. So that's why now in the rest of the study will be to show that we can still have an optimal solution. We distribute the computation and distribute the message exchanges. The other interesting point here is that this minimization in general can be complex depending on what is our starting machine learning problem. And we might not need to find the perfect optimal solution, but the assumption of the paper is that we could even in theory use a randomized method that will solve these local minimizations. So it's a general approach, and the only thing that matters is that every node here solves this problem with a certain uncertainty theta. Let me call that uncertainty capital theta here. Is the uncertainty that I have in the optimal solution at the various nodes, and this is imposed as a design parameter. This uncertainty can be even 0 if the nodes are, if for example these problems are convex, okay, and so we can perfectly solve them. But if we would be non-convex, some complex structure, then we would achieve the optimal solution maybe numerically with an uncertainty theta. And I'm modeling, I mean the paper is modeling this concept with a common theta for everybody. And at this point, if you have, I would introduce the algorithm. Actually, I will not, and I would stop here for a few minutes. We could just start at 11:15 if you agree.